Okay, we are almost there. Okay, let's get started then, since it's 1:30 now. And let me share screen with you. Okay, so today we are going to continue with the study of radiation of a dipole or a short dipole. But before I proceed, are there any questions? Does anybody have any questions? If not, then proceed to what we want to study today. So let me see. Where does it? Doesn't happen. Nothing happens. It's still there. So I like to talk about short dipoles, and before we did this, we actually were studying Hertzian dipole. Hertzian dipole is the case where the dipole is really short. Okay, it's really short, and then you kind of are able to drive a current into this short dipole. And Mr. Hertz, in order for him to drive the current into a very short dipole, he added spheres at the end. Okay, he added spheres at the end of the dipole so that there would be capacitive coupling between the spheres. And so these two spheres look like a capacitor, and then it's a lot easier to drive current into this very short dipole. And we can pretty much assume that the current distribution on the dipole is uniform, because you can assume that the capacitance is large. So if you were to plot the current distribution as a function of x, let's say that this is the x direction, then the current Jx as a function of x will look something like this, almost uniform. Okay, and we say that we can approximate this current J with Hertzian dipole because it's so short that it essentially can be written as a delta function in space. Okay, because it's a point thing, because you can imagine that this thing gets shorter and shorter, and you can make it taller, and then finally it becomes very tall and becomes delta x. That's what becomes of a Hertzian dipole. Okay, and then in order to find the radiation field, we use the fact that A, R is equal to mu the R prime, J of R prime, e to the minus J beta R minus R prime over 4 pi R minus R prime. And if the Hertzian dipole is such that it can be written as such, so essentially it becomes XIL delta R. Okay, so using the shifting property of the Hertzian dipole or delta function, you can actually say that this would evaluate to something like x hat IL e to the j beta R over 4 pi R, using the shifting property that the current is just a delta function. And you can say that this is just mu x hat IL e to the j beta r over 4 pi r, where we have replaced the fact that the magnitude of r is just a distance r. Okay, so if you have a very short dipole, what can you do? Well, you can make approximations. You can make approximations that when you need to do this integral, okay, that the dipole is so short that you need to only integrate the current of the dipole. So you can take this factor out. And then what you need to do then is to integrate this current. Okay, what I've done here is to assume that the dipole is so small and so short that most of the integration will happen around the origin where the dipole is located. And then you can essentially let r prime be equal to 0 and take it outside and need to integrate this over the dipole. Okay, and if the current is now something of this form, say, then you can just plug that in very easily, do the integration. However, if you have a short dipole, okay, the current is not of that form. If you have a short dipole, you don't have two capacitors at the two ends. If you were to inject this and to drive this short dipole with a voltage source, the current would look more like this. Okay, the current will look more like this. And you can say that it has to go to 0 here because of the current continuity equation. Since it's an open circuit, current has to be 0. But then when you drive this dipole, a little bit of current flies or flows in, and you have this, you have the current distribution like this. And then we can actually say that for a very short dipole, you can see that the current distribution looks actually something like this. This is an approximation. Okay, for a very short dipole. But when you plug this into here, you essentially saying that J of R is pointing in X direction with some length delta X. Let me see, it should be something like, if I put it this way, then it would be something like delta Y, delta Z, Jx of X, okay, with something like this, okay? Then you need only to integrate this function. You need to integrate this function, and this integral would become something like A of R would be something like this. And then dx, dy, dz would go away, and then the only thing you need to integrate over is the x. Okay, maybe it goes from minus a to a. Because the other integrations will go away because it's a delta function. And so what you're doing is actually finding the area under this triangle. And that area is roughly given by, well, half the amplitude of the peak times the area under the rectangle. So you can say that a short dipole, when you have the current to be triangular in distribution, can be approximated by a uniform current dipole, okay, of half a length. You can show that this is half a length. Okay, the dipole where this is A over 2 and A over 2 will have the same effective area as a triangular dipole. So you can work this out quite easily. It has been done in the lecture notes, okay? But what I want to talk about is actually the concept of a radiation resistance. Okay, so when you drive a dipole antenna like this, and this antenna radiates, okay, it gives rise to radiation loss. So you should be able to see that the radiation loss is as if this antenna is being hooked up to a resistor. Okay, you can say that a radiating antenna can be approximated by a simple circuit, which looks like this. And then if you calculate the power radiated, the total power radiated by this antenna, you can say that this is the same as half IR squared. Okay, if the current flowing there is I, the power radiated on this circuit is equal to that, and you can equate that to the total power radiated by the dipole, which you know how to calculate. And then from that, you can find the radiation resistance, okay? Radiation should be this, okay? Is equal to 2 power radiated over I squared. Okay, maybe it's better to put the magnitude over here. So this is a concept of a radiation resistance. It's an equivalent resistance that you put in your generator or the driving voltage that absorbs the same amount of power as the antenna has radiated, okay, due to radiation loss. And actually this doesn't happen this way because there are some near field, and there's some near field, and what you have is that you will see a capacitor. Okay, when you just naively drive the dipole with the voltage source, you will see a capacitor because there will be some near field here that stores electric energy. Okay, so in order to cancel this capacitor, what is usually done is that you add an inductor in series with the capacitor. Okay, and you pick it such a way that the LC tank circuit forms a short circuit, and finally this can be thought of as being equivalent to this. Okay, at resonance. Okay, so any questions before I move on to talk about other things?
I have a question on
yes.
Where is physically located that loss of dipole antenna? Where
So
does
the loss of a dipole antenna is due to radiation. And if you compute E cross H conjugate, which is the complex pointing vector, and if you take its real part, which would be half the real part, which is half the real part of E cross H, this is not equal to 0, okay? This is not equal to 0 because the antenna is radiating energy to the far field. And you have to account for this loss somewhat in your circuit model. And oftentimes, we like to connect back to circuit theory. Because circuit theory is the simplest theory that electrical engineers learn in the beginning. And so when you come to a more complicated system, like an antenna radiating, you like to connect back and ask, what is the circuit equivalence I can use to describe this radiation? So this is the circuit equivalence I can use. And actually, before you use that, the antenna has some internal capacitor that you have to tune out. Only then you can use that as the equivalent circuit. So does it make it clear now that an antenna has to radiate? When it radiates, it has some kind of a loss. It's not metal loss, it's not copper loss, it's not wall loss like in a cavity. It's called the radiation loss, okay? This radiation loss can be accounted for by a radiation resistance. Is this clear?
Yeah, I was confused with the terminology, like radiation loss as associated with the loss. I thought about the radiation, like radiated power from the antenna.
Yeah, it's also called radiation loss. Okay. So if you don't have any question, that's a good question, and let me move on to actually first explain why an antenna radiates. Okay. An antenna radiates because as you can see here, the dipole is changing its sign, and after a while, the electromagnetic field gets torn off from the antenna source. And when it gets torn off, it radiates. This is a picture on the left, and I can also show you a picture on the right, where it's more continuous. You can see that as this dipole is changing sign, the field of the antenna gets torn off. Okay, gets torn off, and the antenna has to radiate. Another very interesting phenomenon is called the Cherenkov radiation. Cherenkov radiation is when you have an electron. And if this electron moves, it will radiate, okay? And we can think of it this way. If you have an electron, the electric field looks something like this, okay? Maybe I'm drawing something with a positive charge, okay? So this is a positive charge. And if it moves, then what happens is that the electric field starts to bend. Okay, if this charge moves, and if it moves in such a way that it starts to bend, if you were to draw the potential front of the source, the potential front is going to look something like that. And if the electron moves so fast that they're faster than the speed of light, okay, then something is going to look like this. And what happens is that if this thing looks to be very fast, then the electric field will look something like this. Okay. The electric field will bend and finally got torn off. And it has to start radiating. It will radiate in this direction, as you can see in this picture. This is called Cherenkov radiation. And it was observed in a laboratory many years ago in Russia. And this person was finally given the Nobel Prize because nobody thought an electron should radiate and should radiate in that manner. Essentially, the electric field got torn off when this electron moves too fast. Okay, so let's do some math. To understand this physics. So the first topic I like to calculate is the radiation field. Okay, we studied the radiation field or the far field approximation. Okay, and how can we make approximation so that this can be calculated? As I said before, let me just focus on one integral, the integral for the vector potential, which we find to be this one over here, e to the minus j beta r minus r prime over 4 pi r minus r prime. And I like to make far field approximation, okay, so that I can approximate this thing in here. Right now, as of this point, this integral is very difficult to calculate. You wouldn't want to calculate anything with it at this point because r minus r prime is a very complicated function, okay? R minus r prime would be, well, if I write it out explicitly, would be x minus x prime square plus y minus y prime square plus z minus z prime square, the square root of. It's the distance between the position vector r and r prime, okay? So that is a rather complicated thing, and we like to make approximation. And we like to make approximation when r is much, much larger than r prime, okay? In other words, when this vector is much, much larger than this vector, how can we make approximation to this vector? R minus r prime will be this vector over here, okay? This vector is r minus r prime. Okay, and what can we do to approximate this vector? And you can actually make approximations quite easily. Okay, you can make approximations quite easily. I can show you two methods. Okay, one is to use vector algebra. The other one is to use the parallax method. That is, if I have, say, let me see if I have a picture here. Okay, I do have a picture. Let me see. Let me put this over here. That I like to approximate this function over here. Okay, I like to approximate this function over here. And then what can I do to approximate it? Well, you can use the concept of parallax. That what I'm interested in is the approximate way of calculating that. You can see that r minus r prime, which is this distance, okay, is actually equal to this distance minus this little distance, okay, would be equal to that distance minus that distance. That distance here, okay, is given by r prime cosine theta, which is also given by r hat dot r prime. R prime is this vector. Okay, r prime is this vector. R hat is a vector pointing in this direction from the source point origin to the observation point R. Okay, so you can see that r hat dot r prime is just a cosine of this angle. Okay, and if you take r prime cosine theta, you will get these things. And hence I can also write this as being equal to r hat dot r prime. Okay, so can you see this geometrical argument, which is that if r is very, very far away, these two lines are almost parallel. If that two lines are almost parallel, you can see that the difference in their distance is just this little bit over here. And I can also write this that magnitude of r is just equal to r. Okay, I can also write this formula in this manner. Okay, any questions regarding this approximation? This is called the parallax method. Okay, so if you are familiar and comfortable with this, then I can say that I have this integral. I'm going to make approximation to this exponent over here. And I'm going to make approximation to what I have in the denominator. I'm going to replace those exponent part and the part in the denominator with this approximation. And I'm going to get a new expression for A of r. A of r then would be equal to mu the r prime over the volume of the source, J of r prime. And then the exponent is going to be approximated with r, not r, but just r minus r prime dot r hat, okay? And then that in the denominator, I'm going to approximate as r minus r prime dot r hat. Okay, I'm going to make the approximation which I argue over here, okay? And then I'm going to use the concept that this is in the denominator. This is a small number. R prime dot r hat is much, much smaller than r. As you can see from this picture over here. You can see on this picture, r hat dot r prime is going to much, much smaller than r. Okay. So if that is the case, then I use the concept that if you have a small number, like 1 over r minus r prime dot r hat, you can write this as, well, if you want, you can do a little bit of algebra. Dot r hat over r And this is very small. This is delta. So it's 1 over r over 1 minus delta. And this is just 1 over r 1 plus delta. Okay, by Taylor series expansion. And then I'm going to assume that this is very small. So I'm going to approximate that by 1 over r. But in the exponent, I have to be a little bit careful. In the exponent, I have r minus r prime dot r hat. Okay, even though this is small, I cannot say that it should be thrown out. I can say that I can approximate this as that, but the second term will give me something like beta r prime dot r hat. And I cannot say that this can be ignored unless beta times r prime dot r hat is much, much less than 1. Okay, this is not necessarily true. So let me keep this in the exponent because I cannot say that it is small enough to be thrown out because beta can be large. Beta is omega over c. So if the frequency is large, then the term in the exponent can actually not be thrown out. Okay, let me keep in the exponent. And then if I do that, then my integral that I had previously, with this approximation, this becomes 1 over r. This can be taken outside the integral. This can be broken into 2 terms. This term does not depend on r prime. I can take it outside the integral. And finally, I will have something that this is equal to mu e to the minus j beta r 4 pi r because I take the 1 over r outside. And then what I have left inside is just this integral. And then j of r prime e to the plus j beta r prime dot r hat. Okay. So I can write this in a different way so that it's more suggestive of a Fourier transform. And if I were to write it in a way that's more suggestive of a Fourier transform, okay, I would say that finally what I have is that A of R is mu e to the j beta r over 4 pi r. And then dr prime, j of r prime, e to the j beta dot r prime, where I define beta to be my beta times r hat. Okay, I group the beta and r hat together and call it a new vector. Okay, this is like a 3D Fourier transform. If r prime is x prime x hat plus y prime y hat plus z prime z hat, then beta, I can thought of it as a vector that consists of this thing, z hat beta z. Okay, so the exponent e to the plus j beta dot r prime is just e to the plus j beta x x prime plus j beta y y prime plus j beta z z prime. Okay, can you see that the integral now looks like a Fourier transform integral? Can you see that? Can everybody see that?
Yeah, that's clear.
Okay, very good. Okay, so this is like a Fourier transform integral. But there's one thing that is different from a Fourier transform integral. In a Fourier transform integral, beta x, beta y, beta z are free variables. Okay, but there is something unique over here. If you were to take the length of beta, you take this definition, The length of beta is going to be just beta, which is omega mu epsilon, or equal to omega over c. So the length of beta is always a constant. So even though beta x, beta y, and beta z are free variables, the length of the beta that you can have in the Fourier space is a fixed length, okay? So what you can think of is that I do have a Fourier transform integral, but then in the Fourier space, or the K-space, as some people call it, the Fourier data that I have is restricted to a sphere surface. And that radius, okay, of the sphere is beta. Okay, and this sphere is called a Ewart sphere. Can everybody see that? It's almost like a Fourier transform, except for one difference. The Fourier data is only on a spherical surface. Okay, can everybody see that? It's a peculiar kind of Fourier transform. That beta has to have a fixed length, whereas in an ordinary Fourier transform, beta x, beta y, and beta z are free to be anything. This can be value from minus infinity to infinity. This one can also go from minus infinity to infinity. This one can go from minus infinity to infinity. But because of how we define beta, the beta is a vector of fixed length. So instead of having beta to be of arbitrary length, this vector that we have has to have the length of beta, which is the radius of the sphere in the Fourier space. That is called the Ewart sphere. Is this clear to everybody? No?
Yes.
Okay, very good. Okay, then I can move on then. Let me see. If I move on, then I like to mention the fact that so if you make far field approximation, you can get this, and then what I want you to notice is that in the far field, the field looks something like this. Okay, the field looks something like this, and so what you have is that A of R looks like a spherical wave, e to the minus j beta r over 4 pi r. So this looks like a spherical wave, but then it gets modulated and modified by a function, which I call f of beta. Okay, that function over here, because you're going to integrate over r prime, is eventually going to be just a function of beta alone. It's still a function. It could be even a vector function. Okay, let me put a bar over it. And it's going to be a vector function that depends only on beta. And if you're in the far field, that I show in this picture over here. Okay, let me move this picture up. I'm going to move this picture over here. Okay, so if you're in the far field, what I'm going to say is that if you're over here, if your observation point is over here, if you're going to move your observation point in the vicinity of this far field point, what you're going to notice is the f of beta is going to change very little, because if you're going to move in the vicinity of this point over here, the direction beta, the beta vector or the k vector hardly change direction at all. I don't know if you can see that or not, but what you can say is that if I were to move to a different point, my beta vector is going to change very little. Okay, so what I'm trying to get at is that in the far field, if you keep your observation point to be around here, okay, your beta is going to change very little. However, this is the only function that's going to change very rapidly, especially when beta r is large. Okay, and you can make this far field approximation when beta r is large, and that we see previously, okay, when beta r is large. And that also is the fact that beta is 2 pi over lambda, or it says that r over lambda is large. So if you're far from the source in terms of the wavelength, then this is the factor that varies predominantly. The phase function is the one that varies predominantly fast. 1 over r varies actually quite slowly. Okay, so what you can see is that only this function is changing. So the predominant variation comes from this function, and it's going to be like a plane wave, because e to the j beta r can also be written as e to the minus j beta dot r, okay, because I can let beta be r hat beta, and then my r is x hat plus y hat plus z hat, and this makes it look like a plane wave. So over here, I can rewrite this function, which is a spherical wavefront, to look like a plane wave, and it becomes locally a plane wave. So that's the point I'm trying to get at, is that if you're far enough from the source, everything looks like a plane wave, okay? So you can actually do quite a bit of plane wave physics in the far field. So you actually can use plane waves to study the far field. Okay, and so you know that we know how to calculate A, okay? We know how to calculate. By making far field approximation. And then once we have this, then we can find my H by using Maxwell's equation, or by the definition of the relationship between B and the vector potential A. I can use this. So I can find the far field, but I know that I'm in the far field and this is going to behave like a plane wave. So if you have the del operator operating on something that looks like a plane wave, how can you approximate the del operator? Does anybody want to give a try? What happens to the del operator in the far field?
It's minus j beta.
Very good. Okay, as we said before, a plane wave is described by something like this. And if you have a del operator operating on this, it becomes minus j beta e to the minus j beta dot r. Very good. Okay, this becomes minus j beta. Okay, and Maxwell's equation can be simplified. H, okay, this is the far field approximation, and then I can put j beta cross A over here with a minus sign somewhere. My beta is very simple in the far field. It's just something that points in the r hat direction. And then I can say that this is minus beta over mu with the j out front here with r hat cross A. Okay. Something like this, okay? And then you can actually work this out in greater detail. A, I can write in spherical coordinate system. I can write this out in spherical coordinate system. Theta, A theta plus phi, A phi plus r hat AR, okay? But then when you cross this with the three components, r hat crossing with r hat give you 0 at the end. And finally, you have this to be j beta. Let me just tell you the answer instead of going through the detail. Okay, H is going to be j beta over mu theta A phi minus phi hat A theta. Okay, because r hat crossing with theta give you phi, r hat crossing with phi give you theta. You have this final relationship with the plus sign. Okay, so H can be approximated in the far field to be like this. Very simple algebra, because we're essentially using plane wave physics to calculate the far field. And then you can calculate the E field too, using plane wave physics. From Maxwell's equation, you say that the E field is given by this. Again, using plane wave physics, okay, this is going to be equal to minus J beta cross H over J omega epsilon, okay? And well, you can work this out in detail. It's just straightforward algebra. You'll find that the E field is J omega theta A theta minus actually plus phi hat A phi. Okay. Any questions? I did not do the detail because this is quite straightforward algebra. You replace the delta with the beta. Beta is replaced by this. You plug in this expression for H, and then you do the cross product, you get this. Okay, any questions so far?
To this point, what are the assumptions we made?
This assumption is far field. Okay, the assumption is far field. And then you can go back and regurgitate what far field means. Far field means that I can approximate R minus R prime with this one, okay, with this approximation. And far field means that this distance here is going to be much, much larger than this distance. R prime is the location of the source, okay? R is the location of the observation point. I may as well put an observation point here. I put my eye here, okay? And then as long as this point is so far enough so that this is minuscule, I can use the parallax method and say that R minus R prime equals this, okay? And then I plug it back in to the radiation integral that we have obtained previously. And I have this thing. And I say that, well, I'm not going to throw out the beta in the exponent because it can be large, okay? But I'm going to throw out the small term in the denominator. And then what I have then is that I have a Fourier integral. What I have then is that this is the Fourier integral, and there's something about Ewart sphere and so on. And what do you mean by R being large? What does it mean when R is large? R is large compared to this is one thing, but it also means that this point is far away from this point. But what is the yardstick that I use? What is the yardstick to measure far? Okay, well, there's a yardstick in electromagnetics, which is the wavelength. The wavelength is the yardstick, lambda. So if my observation point is far enough in terms of the wavelength, then I can make this far field approximation. And I also have the argument that if I'm far enough in terms of the wavelength, then the wave looks locally like a plane wave. Looks locally like a plane wave. And if it looks locally like a plane wave, then I can replace the del operator with J beta and makes all this nice approximation that arrive at this simplified formula quite easily. Okay, is this clear?
Yeah, I have another question.
Yes.
How did we get from, at the beginning we had the spherical wave, and there was an integral where we all of a sudden we've got the plane wave. How did we transfer from?
We actually approximate this thing in the exponent with the spherical wave, okay? With the spherical wave. And the spherical wave looks like a plane wave if you're far enough. spherical wave looks like a plane wave if you're far enough. So how far is far? What is a yardstick to use? The yardstick is wavelength. So if I move myself far enough from the source, the field is going to look like a spherical wave. The spherical wave is going to look like a plane wave. If you're far enough, like if you have a spherical wave, it's going to look like this. And if you go very, very far away, okay, it's going to look locally like a plane wave. How far is far? You use yardstick as the wavelength. If this distance is far in terms of wavelength, then a spherical wave becomes like a plane wave. I actually have a nice picture here. This is the FDTD simulation. Finite difference time domain simulation that you will learn later on in the course. This is the waveguide with a hole. Okay, the hole leaks radiation from the waveguide. If you're close to the source of radiation, the wave looks like a spherical wave with a small radius of curvature. But if you go further and further away, then the far field looks like a plane wave. Essentially, the surface of the Earth looks flat because the radius of the curvature is very large. Okay, a spherical wave becomes a plane wave if you're far enough from the source region. Does that make sense?
Yeah, but my question was more about we had the spherical
Yes.
wave, which is 3D case, and
Right.
here what you show is 2D case in which it's radial wave. I mean, in radial case, in 2D case, it's clear what the plane wave is. But how do we approximate 3D spherical wave by a plane wave?
Can you also think 3D? This picture is drawn in 2D, okay? This picture is drawn in 2D, and it's a lot easier for us to draw pictures in 2D. You can think of this as being a 3D picture, and we're just taking a cross-section of a 3D picture, and it looks 2D. When you think of it this way, if you have the Earth's surface, the Earth's surface is a 3D sphere. And if you sit on the Earth's surface and look at the ground around you, it looks flat. Okay, it doesn't have to be 2D, it can be a 3D effect. Anything that is far enough from the radius of the Earth will make the Earth's surface look flat. So even though if you have a spherical wave, okay, you have a spherical wave, and if you go far enough away from the center of the source where the wave is coming out, this wavefront is going to look flat. Does that make sense?
Yeah, that makes sense.
Okay, it makes sense, right? Even as long as you think of yourself being sitting on the Earth's surface, okay? Even though all these pictures are 2D because we can only draw 2D pictures, okay? So because when you're in a far field, the spherical wave behaves like a plane wave, we can do a lot more plane wave physics, okay? Plane wave physics being the fact that the magnitude of E over the magnitude of H is the intrinsic impedance eta, which is 377 ohm, okay, in free space or vacuum. Okay, and if you don't believe me that this in fact is a ratio, you can go through the approximations that we have here. Okay, you can take the ratio of these two terms. You'll find that the ratio is in fact, it's quite easy to take the ratio. You take the magnitude of this field, eta a phi squared plus a theta squared, and then the magnitude of this term. And then you take the magnitude of these two terms, and then you take the ratio, okay? And if you take the ratio, you can find that the ratio is eta. Then you say, aha, why is that so? Why is the ratio so simple? Then you go back and look at the physics again. Well, in the far field, the spherical wave is going to look like a plane wave, and this essentially is plane wave physics, okay? So you find that this is to be true, and this number is sometimes written as 120 pi ohms, okay, for ease of remembrance, okay? You can also find the Poynting vector in the far field, then S is going to be E cross H. Instantaneous one, you can find the complex one, which is E cross H conjugate quite easily. Okay. And then the time average pointing vector is going to be half the real part of E cross H for a time harmonic signal. This is, we have proven this before for time harmonic signal. This is true. Okay. And then you can actually work this out, and you find that plane wave physics would prevail, and that you can find that this is approximately equal to half 1/2 E squared. Okay, this is plane wave physics coming up. Okay, and this is actually predominantly pointing in the R hat direction. And then you can say that, well, S of, if I call this S of R hat, then you will find that S of R is proportional to the product of E squared. Okay, E is proportional to, well, E is proportional to this, but A, if you look at A is proportional to 1/R. Okay, which means that A is proportional to 1/R. We also say that E is proportional to 1/R. E squared is proportional to 1/R squared. So this SR is proportional to 1/R squared. And that is important for energy conservation, because energy or power density has to drop off as 1/R squared in order for energy conservation. Okay. And you can actually find the total power radiated as we did before. You will find that this total power is just the integration of this thing from 0 to pi, 0 to 2 pi, R squared sine theta d phi, and then SR is a function of theta and phi here. And then you will find that this is the total power. Okay, you can do that for any antenna as long as you know how to calculate this quantity. As long as you know how to calculate this quantity in the far field, and in the far field you can make approximations, and that quantity can be calculated quite easily. Okay, and then you can again go and define a directive gain function. The directive gain function. And that will be defined by G, as we have done for a Hertzian dipole, will be this radiation pattern divided by S average. Okay, where S average is the average pointing vector, is a total power divided by 4 pi R squared. Okay, and we can go and calculate the kind of things. And that function can be used to study the property of different antennas. Like if I were to have a, for instance, let me move this up here. Okay, so if you were to study this function for an antenna array, which we are going to study in a little while, the antenna array can be used to focus the energy of the antenna in the main lobe direction, and there will be some back lobes and side lobes and so on. And you can make the antenna more directive as a result, okay, by putting different kinds of sources. We study array in a moment, and here's another antenna array called the 5G array. And using that, you can actually calculate the radiation pattern, this function, which is rather complicated, and then you can see how to focus energy. Okay, so the next thing I like to study now is actually antenna array. Let me just skip a little bit here. Okay, so I'm going to study antenna arrays, and I will first start with the linear array of dipole antennas. Do the far field approximation and find the radiation pattern of an array. So let's begin with the first antenna array using dipoles. And we're just using simple dipole. And for simplicity, we can use Hertzian dipole. Okay, so if we put some dipole array, what can happen is that each of them would emanate a spherical wave. Okay, and then they would add constructively or destructively in a certain direction. Okay, and we can adjust the phase of this antenna so that they act constructively or destructively, constructive or destructive interference. And then we can use this array to focus the energy of the antenna in a certain direction, and it's what we are going to study next. And so we can calculate the far field. Far field of this array is, as we said before, after we make the far field approximation, is given by this thing. And then it is just given by, I'm just going to use one integral, okay? And then this phase factor, r prime times j of r prime, okay? I'm going to make things simpler. I'm going to assume that this dipole is going to be something that is made of Hertzian dipoles in the r direction or in the x direction. So jr prime is going to be something pointing in the z-axis that is pointing out of the paper. This can be out of the paper, and then this can be z, or maybe this can be my y. Okay, actually this should be wrong. Y should be pointing inward. Okay, so my dipole array will consist of a current at the origin. Okay, x is equal to 0, and then another one at x is equal to 1, x minus d1, and then another one, x minus d2, blah, blah, blah. You can add as many as you can. And then this is 0, 1, 2. This first distance here is d1. The second distance is d2. Okay, and then I can multiply this with delta x, sorry, delta y, delta z. So that makes each of them into a Hertzian dipole. In essence, mathematically, I'm just putting a linear array of Hertzian dipole. This is called a linear array. Okay, of Hertzian dipole. And then if I were to plug it into this radiation integral now, we plug this into this radiation integral in the above, then I'm going to see some simplification that the vector potential A of R is going to be, I can take the current element out, okay, 4 pi R. Okay, and then I'm going to put my mu somewhere here. Maybe put the mu here. And then the phase factor is going to be out there. Okay, I'm going to have a phase factor, and I'm going to do this integration. Okay, the integration is going to be something to do with the fact that this very complicated I'm going to have this complicated thing in there, and let's just put it in there, and then I'm going to multiply with this factor. Okay, this factor beta dot r prime, and then do a dr prime. Okay, I'm going to do this integration. R prime is going to be the location of the sources. Okay, you can see that R prime is going to be x hat x prime, because all my sources are located on the x-axis. Okay, then I'm going to make beta. Beta is equal to r hat beta. Beta is pointing in the direction of the observation point. R hat, if you recall, is the direction of the observation point. Okay, if you recall previously, okay, R hat is not given here, but given in this picture. R hat is the direction of the observation point. Okay, so if I remember what those things are, then I can go back and say that beta dot r prime is just equal to beta x prime r hat dot, sorry, r hat dot x hat. Okay, it's going to be just that. But I'm going to make some simplification. I'm going to assume that the observation point is in the xy plane. Z is pointing out of the thing. And my dipole arrays are pointing out of the paper. Okay? And they are located in the x direction. And r hat dot x hat is pointing in this direction. R is pointing in three-dimensional direction, but let me make life simpler. Let's make my R to be in the xy plane only. So this would be something like x hat plus y hat. Then r hat dot x hat would be equal to r cosine, let me see, this is phi, okay? This length is r, okay? R cosine phi. I think that's what I get. I should get just r cosine phi. Okay. No, it's not. It's sorry. It's x cosine phi. It's just cosine phi. Sorry, just cosine phi. R hat dot x hat is just cosine phi, so that beta dot r prime is just going to be beta x prime cosine phi. Okay, that's what I'm going to get. And then this exponent here is going to be simplified. And then I plug in all the delta functions that I have from the previous slide. And now I can do the integration. And if I do the integration, then what I should get is that A of R now should be equal to Z hat with a mu out front, IL over 4 pi R, a spherical wave. This is just a spherical wave. And then each of this term will integrate with this function, and then each of them is a delta function. And I use the shifting property of the function. Okay, I'm going to get A0, A1, and A something. I'm going to make a simplification that A sub n is just going to be e to the j n psi. Okay, and previously I have A0, A1, and A2 been different from each other, and then I'm going to assume dn to be n dn, so that the array is equally spaced. If it's equally spaced array, then the series that I should obtain is j beta d plus cosine psi. Let me see, cosine phi, sorry, cosine phi plus psi. This is the first phase that comes from A0, okay? And then the second term is going to be e to the j beta d 2 because of this equally spaced array. And then the second one is going to be 2 psi because equal phase. Okay, this is equally linear phase. This is called linear phase. The phase is just going to increase linearly, and the array is going to be equally spaced. And then you can add the other series. And that is the series of the A that you should sum up. And you know how to sum this up because the first term is 1, the second term is x, the third term is x squared, the third term will be x cubed, because I deliberately choose the phase to be such so that this series becomes very simple. And I can actually sum it up. Okay, if this is n term here, okay, if this is n term, I can actually sum this series up very easily. Okay, if the last term is x to the power of n, and if I were to sum this up, then I get something that looks like this. Let me see. Okay, I'm going to use the fact that 1 over 1 minus x is 1 plus x squared plus x cubed plus something. It's an infinite series, go to infinity. And then if I'm going to have xn over 1 minus x, then there will be xn plus xn plus 1 plus xn plus 2 equals to infinity as well. But if I'm going to subtract these two series, I'm going to get a finite series 1 plus x squared plus x cubed plus xn, okay, will be the last thing, will be 1 minus xn or 1 minus x, okay? So I can sum these two series up and then subtract them, and this is the expression for a finite summation, okay? And this last term is actually xn minus 1 over here, okay, since it begins with xn. So you know how to sum this series. And actually, you can go to the algebra and look at the vector potential. You can sum it up. It actually would be proportional to mu z hat IL over 4 pi r e to the minus j beta r. And then if you use this formula to sum that series up, it would be something like this, okay? J n beta d cosine phi plus psi over 1 minus e to the j beta d cosine phi plus psi. Okay, the algebra is kind of laborious, but it's doable. It's something that you might have done in the signal processing course. Okay, in the signal processor, there's some series like this all the time. And then you know how to find A. And then if you were to plot this, okay, this will be a complicated function of phi. In this case, because we do it in a 2D space, because we restrict our observation point to be on the XY plane. So this will only be a function of phi, okay? And you can choose psi. Psi is the phase. Psi is the phase between each element, okay? It's a linearly phased array. So you can change this array. This is called the array factor. And you can engineer it. You can engineer it by picking the spacing, picking the phase, okay? And you can actually get this pattern to be directed in different directions and so on. So are there any questions so far before I move ahead? so you can actually plot this array factor. That part is actually engineering. Okay, this part is actually engineering. So what I want to show is that you can actually engineer different kinds of pattern. In the XY plane, you can actually get patterns that looks like this, and then you can get patterns that looks like this. Okay, patterns that look like this by proper engineering. And why do they look like that? It's all because of constructive and destructive engineering interference. Okay, and an array that is like this, okay, is called an end-fire array. This is because it essentially radiates in the end-fire direction. And this direction is called end-fire. The other direction is called broadside. And similar, you can pick the phase in such a way that it radiates in the broadside direction. This is called a broadside array. Okay, this is called a broadside array. And if you're a very good signal processor, you would be able to identify the fact that this function is very much related to something called a digital sync. Okay, how do we see that this is a digital sync? Well, we have to do some algebra. We have to do some algebra to show that this is a digital sync. And let me show you the algebra. Okay, so essentially the radiation field pattern, the far field vector potential is proportional to this function over here, Jn. Let me call it a function x, okay? 1 minus jx. Essentially it's something where x is that complicated thing in the exponent here. Okay, I just call that complicated things x, and then you can do tricks like, well, I can take out e to the minus jnx over 2, and then I put it back in again, jnx over 2. That essentially becomes 1. Okay, and then if I do that, I will be left with let me see, I should take out a plus and put a minus here, and then I should have nx over 2 here. That is what happens to the numerator. I can do likewise in the denominator, e to the minus jx over 2 minus e to the jx over 2. Okay, I'm supposed to take the magnitude of this thing, and you know that magnitude of products are products of magnitude, so this thing goes away. And then the function that looks like that can be combined into a sign. Okay, this thing can be like a sign, and this thing can be combined into a sign. And you have to take a factor of 2 somewhere out there, but essentially all of them becomes sine function with those factor canceling out. This becomes 1, this becomes 1. You take up some imaginary number, it has magnitude of 1. And then you have this function. Okay, this function is called digital sync. Okay, so if you were to plot the numerator of this function, well, how does it look like? Well, a sine function is going to look sinusoidal. Okay, let me elaborate more on this function. Okay, so if you were to plot, say, n is equal to 3, you have 3 elements in the array. Then if you were to plot sine of 3x over 2, okay, so when x is equal to, let me see, when x equals to pi, and then it's going to go to 0. So this function is going to look something like this. Okay. So when x is equal to 2 pi over 3, so this first point is 2 pi over 3. Okay, and then it's going to be periodic function. So it's going to look like this. Like this. And it was going to repeat itself that way. I'm going to plot the magnitude of this actually. So this is sine of 3x over 2. Okay, and then the denominator is going to be sine of x over 2. Well, it's going to go to 0 when x over 2 is equal to pi, and x is equal to 2 pi. Okay, so this is 3 pi over 3, and then 2 pi is going to be, well, that means that 2 pi is going to be here. Okay, x is equal to 2 pi over here. So the denominator is going to look like this. And then it was going to look like this. Everybody agrees? This is sine of x over 2. This other one is going to sine of 3x over 2. Agree? Everybody agrees? So this is going to repeat itself. Okay? Because these are all periodic functions. And over here, we have a difficult point. Over here, both the numerator and the denominator goes to 0 because I'm plotting this. I'm plotting this function. I'm plotting sine of 3x over 2 divided by sine of x over 2. Okay, and over here, both of them are going to be going to 0 simultaneously. Does anybody know what we have to do and how to evaluate this function when both the numerator and denominator go to 0? Both of them go to 0. What do we do? If you have learned from any of our engineering courses before, if numerator and denominator both go to 0, what do you do?
So we take limit and we use the Lapitas law.
You use Lapitas rule. Okay, that's one good thing. What other choice do you have? Actually, there's another difficult point here, which is here. Both numerator and denominator goes to 0. You can use Lapitas rule. And what is the other rule that you can use?
Could you look at the left and right of that point? Because that means there's a hole on your graph.
Right, right. You can look at the point slightly to the right and slightly to the left. Then slightly to the right, yeah, very good. That's a correct thing to do. Slightly to the right and slightly to the left, numerator and denominator does not go to 0. But I can get as close to the origin as possible, as close to the origin as possible. And yet the numerator and denominator do not go to 0. But I can do Taylor series expansion when x is small, okay? So when x is small, I can do Taylor series expansion of this. On the numerator, I get this. And then in the denominator, if I do the Taylor series expansion of this, I get x over 2. So this is actually 3. Okay, so you can apply Lapitas rule. Okay, Lapitas, I hope you still remember. Lapitas rule that you learned in high school. Okay, the French don't pronounce their S, so we call it Lapitas rule. Okay, and there's a story behind this rule, which is that Lapita, or this person who has this rule named after him, actually bought this rule so that he got himself named after this rule. That was the story I heard. Okay, but Lapita means hospital in French. Okay, but I don't know why this guy has a name of Lapita. So just the simple fact that instead of using Lapitas rule, you can also do Taylor series expansion and get the factor of 3 very easily. You will also get a factor of 3 here if you do Taylor series expansion. So what happens is that you have numerator going to 0 very rapidly at this point. The denominator goes to 0 only at this point. So what you have is that if you plot the ratio, if you plot this, it will be something like 3, okay, over here, and then it goes to 0, and then it becomes 3. Okay, it goes to 0, and it becomes 3. Okay, so this function, when you plot it, will look something like this. This is called digital sync. If you're a signal processor, you work with this kind of function all the time. It's almost like the sync function, the other sync function that you might have learned. Okay, this function sine x over x is called a sync function. Okay, this function will look like this. Okay, it only has one peak. The digital sync has a peak and then maybe another peak. I'm just plotting the amplitude. Okay, another peak. And this is what the signal processor called aliasing. Okay, because of aliasing, in fact, you have images or aliasing images. I don't know how many of you are signal processors. You get this kind of repeated signals, and you get this in antenna array, because the reason why you get this in antenna array is because of this fact. The fact that the field is related to the far field is related to the source by a Fourier transform. And in signal processing, you play around with Fourier transform all the time. So now if you put in a set of point sources, you're almost like sampling the current source with point sources. It's like digital sampling. It's like digital sampling. And if you go to the math, you get the digital sync coming up, and you have all this array pattern. So if you know signal processing, you can play around with this engineering quite easily. I'll let you go because I ran over time, okay? Are there any questions before we stop here? Are there any questions? If not, I'll let you go then. Sorry that I ran over.
Quick question.
Yeah, go ahead.
Why do you call that sine 3x over sine x like digital sync function?
Yeah, we call it digital sync. You asked me why we call it digital sync.
Yeah, it doesn't look like sync. Sync is the sine x over x, right?
Right. Yeah, here is digital sync. Here is the sync. Okay. So they look different. The difference is that in the real sync function, the denominator is not a periodic function. But in the digital sync, both the numerator and the denominator are periodic functions. So at places where both of them go to 0, you have a peak. Okay?
Yeah, I see. That's clear. Thank you.
Okay. Any other questions? If not, I'll let you go. Okay, so you can see that antenna array is a very rich area. It's where your wireless communication knowledge comes from. You need this array for wireless communication. You need them for 5G antenna design and all kinds of antenna designs. Okay, I'll let you go. Okay, thank you for coming. Okay, bye-bye.